Safety is one of the most important performance attributes for all car makers, and the objective is fairly straightforward: protecting occupants inside a car in accidents. But it also extends to the protection of those on the outside: pedestrians, cyclists, and emergency services responding to crashes. Reducing the risk of injury and ultimately saving lives is achieved by the deliberate design of the base platform a car is built from, the parts, components and control systems within the car, and careful tuning of the safety restraint system. Safety performance is objectively measured through destructive and non-destructive tests conducted on full vehicles, subsystems, and even individual components. The logic that shapes the philosophy of safe car design can be split into four segments. The first is prevent, by engineering to avoid crashes and make cars uncrashable. Number two is prepare, by engineering the car's active and passive operating systems to keep the driver in control in all circumstances, to reduce the severity and the frequency of crashes. Number three is perform, by optimizing the factors that influence injury risk reduction for occupants and for pedestrians. And four is protect, by improving the outcome of the crash to make sure that when the dust settles, the dangers are over. Safety engineering incorporates countermeasures for each segment, with the safest cars optimizing all four, but that can only be achieved when the principles of safe car design are incorporated throughout the car. Let's look in more detail at how cars are designed to prevent crashes, and when crashes can't be prevented, the engineering factors that can prepare pre-impact. Today's cars already support drivers with features that provide a host of warnings and important driving information, and many can intervene with emergency brake and steering overrides when required. But the safest car is obviously one that prevents accidents by completely avoiding crashing. To try and engineer that outcome, the automotive industry is focusing on developing automated driving, to try and eliminate driver decision making and reactions. The relative capacity to automate driving has been defined by the Society of Automotive Engineers into 6 levels. From no autonomy at level 0 through to level 5, where a car can drive itself under all conditions. Automated driving has already demonstrated its value by avoiding, or at least reducing, the severity of real crashes all over the world. The ultimate vision for rule makers and for car manufacturers is to eliminate the risk of serious and fatal vehicle crashes, with autonomy's goal being to achieve that before level 5. When crashes can't be prevented, safety design can influence the outcome by preparing the circumstances pre-collision to reduce the severity. A human driver's potential for a crash can be affected by the foundations of their car's design. Grip, weight transfer, ride quality, and handling performance combine together to determine a car's dynamic behavior. Dynamics is dictated by the mechanical design of the suspension, the steering, and the brakes, along with the tuning of their respective actuation and control systems, all of which contribute to the driver's control over the machine in all sorts of manoeuvres. A car's stability, predictability, and responsiveness directly affect crash risk and crash severity. Different vehicle types have their own individual dynamic safety requirements. For example, SUVs have a higher risk of rollover than smaller cars as a consequence of their mass and their higher center of gravity. But all cars' dynamics is affected by the number of passengers, the cargo weight, and cargo location, and will change completely when that car is towing a trailer. Therefore, safety design has to ensure that in all circumstances the driver maintains control, and by doing so, the risk of crashes is reduced. Therefore, it is fair to say that safety starts at the tyres. ADAS, Advanced Driver Assistance Systems, optimize the response to emergency situations by providing clear warnings and/or intervening during manoeuvres. Primarily, the systems optimize the reaction and control over the engine, the brakes and the steering. Vision and object detection sensors fitted around the vehicle detect obstacles. Drivers of modern cars are familiar with the warnings from blind spot monitors, reversing cameras and parking sensors. More complex systems are able to communicate speed limits and road sign information, often using multiple cameras, which can be used to read lane markings to prevent inadvertent wandering into traffic. The most sophisticated systems are able to detect pedestrians and cyclists that can often be invisible to the driver. Sensors inside the car are also able to automatically warn the driver when they're distracted, or even when they're tired. By interacting with the way that power is delivered to the driven wheels, traction, stability and slip control systems prevent loss of grip. Controlling the power delivery also allows adaptive cruise control to maintain the driver's desired road speed, and at the same time automatically responding to traffic conditions to maintain the gap to the vehicle in front. Enhancing that system provides traffic jam assistance, which controls acceleration but adds braking in slow speed traffic. Integrating ADAS control logic into the braking system ensures that wheel lockup is avoided even on the slipperiest of surfaces or steepest of inclines. Hill descent control uses automated braking to maintain speed and control even in the toughest off-road and low-grip conditions. Autonomous emergency braking, AEB, adds in vision and object sensors to automatically apply the brakes if the driver doesn't respond to an obstacle, whether it's a machine, a person, or an animal. To ensure optimal stopping power, pre-brake conditioning systems pressurize and dry the brakes to provide immediate, rapid stopping power. The brakes can also be used to keep the car going in the right direction, and where necessary, directing the car back on track by applying brake force to specific wheels. ADAS steering control actuation assists obstacle avoidance by directing the car around detected objects. Lane change and support systems can maneuver the car into a free lane, for overtaking for example, or equally to maintain position within a lane to avoid accidentally drifting into traffic. For convenience, some cars are available with self-parking systems, and the most advanced of those systems can even help the driver to maneuver while they're towing. But even the best ADAS and the most sure-footed chassis can't guarantee against accidents. Therefore, safety engineering has developed techniques that pre-configure the car to try and optimize crashworthiness when a collision can't be avoided. Control may be added to the seat belts to position the occupants correctly within their seats. The seats themselves may be automatically moved to a more crash-friendly position, and some can even adjust the headrests and the bolsters to improve protection. The steering wheel and even the pedals might be moved away from the driver, and windows and sunroofs closed to prevent occupant ejection or debris entering into the cabin.